Our next speaker is Roger Penrose, who's going to tell us about the conformal cyclic cosmology. Roger, are you,
Hello. Yes,
are you
I'm
ready?
here.
Fantastic. Please go ahead.
This talk will be mainly pictures, or entirely pictures, perhaps I should say. There are equations, but I really want to give the important main ideas. First of all, I want to point out the effects of curvature. First of all, in the slide, we see somebody falling freely in the Earth's gravitational field. There will be this distortion. This represent, you imagine a circle, and this will get distorted into an ellipse. And that's the effect of the Weyl curvature. So it squashes in one direction and stretches in the other direction. Can I have the next slide, please? I will be mainly talking about light rays and the effect you see here, looking at the deflection of light due to the sun. And we see a circular pattern of stars would be, as it moves outwards, the displacement outwards gets less and less the further away you are out from the sun. The transverse directions get stretched outwards. So you see that a circle gets distorted into an ellipse. And this is the effect of the Weyl curvature. Can I have the next slide, please? In space-time terms, you see at the top an observer looking back. The Weyl curvature produces this distortion, and the Ricci curvature produces the positive focusing. These effects are essentially what I used in the proof of the singularity theorem, which eventually seems to have won a Nobel Prize. The Weyl curvature gives this distortion effect. It's always a positive focusing inwards if the energy flux across the light ray is non-negative, or it's positive, that you get a positive focusing. If you have Weyl curvature, initially it's zero net focusing, but once you have the effects of different Weyl curvatures at different distances, the residual is always positive focusing. This is the Riccaduri effect, and it's basically what I relied upon, is that you have a net positive focusing on light rays. But the important point I want to make is that there are these two kinds of curvature, and they have a very different effect. One has to think of the Weyl curvature as the analog of the Maxwell field tensor, and the Ricci curvature, that's the rest of it, as the source, that would be the charged current vector. In Maxwell theory, they're different order of derivative. In the spin 2 case of gravity, they're the same order of derivative. So you see the Weyl curvature, which represents the free gravitational degrees of freedom, and the Ricci curvature, which represents the sources. So the entire curvature splits into these two, 10 components each. Actually, for light rays, you only see 9 of them because the scalar doesn't produce any effect on the light rays. Okay, so you see these important two effects of curvature. Now, can we move to the next slide, please? This was the picture taken from my paper in Physrev Letters, which, as I say, seems to in 1965. It was a proof that in general, if you have the bottom we have a Cauchy surface, and you put data on that, and the matter starts to collapse inwards, and in the exact Schwarzschild case, or if you could say this is like the well, the Schwarzschild case, but we have some matter falling inwards. And just outside, when you get inside the horizon, you'll imagine this little ring here is what I call a trapped surface. You must imagine, of course, there's one more dimension. So it looks like a ring. It's actually a two surface. And the effect of it being inside the horizon is that you get the focusing inwards, both for the inward rays and the seemingly outward rays. They're also inwards. But the important point is that you get an inwards focusing. And once you get that, we have this Riccaduri effect. It keeps on going. Of course, the argument is complicated because you might imagine it's not this simple symmetrical case, and it could be irregular. And that was the whole point of the proof, that in irregular situations, you still get a problem with this future of that. Now, so that, what I call the trapped surface, the boundary of that, you see it has to be a a compact region, and that leads to a contradiction. I won't go into that. I just wanted to point out the role of the Weyl curvature as being the central thing. This diverges to infinity. The Ricci curvature is zero if you're in vacuum outside here anyway. The important point is the diverging of the Weyl curvature. I should say that the work of the Russians, Lifshitz and Khalatnikov, in the initial work, there was an error. I wasn't aware of that, but I felt you had to look at this problem independently. But when Belinsky got involved as well, the error was corrected. And you can see from their analysis that you get very wildly diverging Weyl curvature when you get into the near singularity. And that's quite plausibly a generic kind of picture. Okay, let's move onwards to the next picture, please. Now, this is just a cartoon of the universe. You might ask, why don't I put inflation in here? I'll come to inflation a little on. You can imagine it's there or not. It doesn't make really any difference to the picture. The picture, we have this exponential expansion in the future, which we're just beginning to see. I've drawn the picture ambiguously as to whether it's spatially closed or open. It's hard to draw if you have an open model. So I'm pretending it's sort of closed to begin with, and maybe it keeps on going, maybe it's closed or open. It doesn't make any difference to the arguments that I want to give. There may be detailed differences in the calculations, but I'm not going to talk about that here. So we have this exponential expansion, which is we're just beginning to see. And this, in my view, is the effect of the cosmological constant. Cosmological constant plays an important role when one does start to write down equations for what I want to say later. Okay, move on to the next slide, please. Now, the thing I want to discuss here is I produced my singularity theorem, and then Stephen Hawking quickly picked up on it and applied the arguments to the Big Bang to show that in the singularities were also generic in the Big Bang. Now, I was puzzled about this very much because if you have a collapsing universe, this is a picture of a collapsing universe, time is going up in my pictures normally, and you imagine that you have certain irregularities. It's not exactly the very symmetrical smooth case, and you would get various collapses to black holes and things like that, and they would congeal with each other, and there would be one unholy mess at the end, where the Weyl curvature just simply goes wild and diverges to infinity. So this is the general picture we would expect for a generic collapse. Closed or open, that doesn't make much difference here. Now, can I have the next picture, please? The question arises, why wasn't the Big Bang like that? You see, you can actually do some calculations here and work out, take the collapsing case we were just looking at before, and we can look at the entropy in the black holes and use the Bekenstein-Hawking formula. And we find that the entropy is completely dominated by that in the black holes. And you can see that the phase space was absolutely, the amount of phase space for our smooth collapse would be ridiculously tiny compared with the amount for the generic case. And you can make some estimate of that. It's like something like 1 part in 10 to the power 124. The 10 to the 124 comes from the total entropy of the black holes and what we see in the universe, including the dark matter. And this just shows how incredibly unlikely the situation we find. So why is it that we don't see that very smooth situation that I showed you earlier? Now, of course, people talk about inflation as an argument against that. It doesn't really make any difference to the picture I showed you just previous to this. You can put in the inflaton field in it or not, and it makes absolutely no difference to the picture. Inflation only makes a difference when you're very close to a Robertson-Walker-Friedman model. In the general case, it hardly makes any difference at all. So it's not the answer to this question. Can I move to the next slide, please? The issue that I'm raising here now has to do with the second law of thermodynamics, which is very crucial to all this. We have a very low entropy at the beginning. I'm imagining here we have the top 3 pictures represent a gas in a box. And we imagine that the gas is initially constrained to be within a little region here. You had a little box and you open the doors and the gas spreads out through the box. And this is the natural thing you will get. Uniformity increases as time increases, and that's the increase in entropy. Now, the bottom three pictures, we imagine a huge galactic box, galactic scale box with stars running around. And because of the universal nature of attractive nature of gravity, you start to get this clumping. And again, with entropy increasing from left to right, time going from left to right, you get the completely opposite picture. You get a clumping and clumping and clumping, and then you will get black holes forming where the entropy shoots up enormously. So increase of entropy is left to right. And what we see in the early universe is uniformity, very close to uniformity, which is like top right and bottom left. Very strange. It's not just the entropy was low. It was in the beginning, it was low in gravitational degrees of freedom. It's a point I've been making for a long time. Can I have the next picture, please? This is even more striking because when we look at the, I think it was the Kobe satellite, and this is the picture of the intensity of the radiation, microwave background radiation. Bottom is the intensity, the bottom is the frequency, sorry, and the top is the intensity. And you see this beautiful Planck curve where these error bars here are exaggerated by a factor of 500. So you see the Planck curve is really hugged to within the thickness of the line. Even the last one, if you go down by 500, is still hugging this Planck curve, which tells us that what we're seeing in this microwave background is something very, very close to thermal equilibrium, a point which is often made. But this also is a sort of paradox because you're going back and back and back in time. And second law of thermodynamics says entropy should be going, as you go back in time, it should be going down and down and down until you seem to reach a maximum. Very strange. Of course, you may say the universe is expanding, and maybe that's the answer. It's not the answer, as you can see quite easily. The answer is that the radiation and the matter were very close to being in thermal equilibrium very early. Yet the gravitation seems to be completely divorced from this, and the initial state was free of Weyl curvature. The point I want, can I have the next slide, please? Yes, you see, the point is that in the space-time singularities, we have this very, very curious asymmetry. You see, as with other people, I used to think that the solution to the singularity problem is quantum gravity. And quantum gravity is certainly what you would have to consider when you regard the collapse situation, when you get enormously high curvatures. And maybe the answer is that you have to get into, when the radii of curvature get down to the Planck length, you might expect that quantum gravity plays an important role. Very likely, I have nothing against that. The point I am making that it's not the answer. It's not the answer to what we see, because what we see is this very strange imbalance between what we would expect to see in a generic collapse and what we seem to see in our universe. We seem to see very low Weyl curvature. In fact, I made the conjecture, this was a sort of postulate or well, I'll just say that the Weyl curvature was zero in initial singularities without any justification from quantum gravity. I used to think maybe quantum gravity was a very, very strange theory in which unitarity was completely violated, and it wasn't a normal quantum gravity theory, and maybe it explained why the Weyl curvature was zero. And eventually I gave up on that and just postulated that the Weyl curvature should be zero in the initial state. It's not an explanation that comes from quantum gravity. I don't see how quantum gravity can supply you with this very, very extraordinary difference. It's not emphasized for some reason by other people, but it's what we seem to see in our universe. Why was the Big Bang such a strain? And I should say again, inflation does not resolve the problem. You could put inflation into the picture, and the generic situation is very, very similar to what we had before. Can we have the next slide, please? Now I want to talk about this from a different angle. Here we just have a picture of a null cone locally at a point, and I want to just express how the metric is basically the, you have two particles, massive particles, and you have to have not just the light cone or the null cone, but you have to have these bowl-shaped surfaces and hill-shaped surfaces. These are the equal times for different space-like particles. That's combining together the two most famous formulae of 20th century physics, E equals mc squared, of course, and Max Planck's E equals h nu. Put them together, it tells you frequency and mass are equivalent. So if you have a massive particle, it really is a clock. What about massless particles? Next slide, please. That, of course, doesn't even hit the surfaces. It doesn't even notice the passage of time whatsoever. It's just interested in the null cone. Next picture, please. In fact, when you have massless things, not just particles, but the Maxwell equations as well, the Maxwell's equations are completely invariant under change of scale. What the structure is the light cones. Now, the light cones are the conformal structure, and it's more important than the metric structure, in my view. The metric structure is secondary, and it's when you have mass that you go to the metric structure. But when you have no mass, the conformal structure is the important thing. Can we move to the next slide, please? This is another feature of looking at the conformal structure, is that you can talk about infinity. It's a trick I used to use many times to talk about the infinite, how to talk about infinity and how radiation and that sort of thing when you have asymptotically flat spaces. This picture is an Escher picture, which shows very nicely how hyperbolic geometry, don't worry about that particular geometry, but hyperbolic geometry of the plane, the infinity, can be represented by this nice smooth boundary. It also illustrates conformal because you see the eyes of these fish creatures. The closer they are to the boundary, they remain circular. Conformal means you squash in one direction, you have to squash in all other directions by the same amount. In relativity theory, it means you preserve the null cones. That's the essential point. Okay, can I have the next slide, please? Now, you see, that allows us, particularly now that we have a cosmological constant, or what we call it, dark energy or whatever, I like to call it a cosmological constant because the theory is very clear. Einstein's equations with positive cosmological constant. And there are nice theorems due to Helmut Friedrich in particular, where he shows that in generic situation, you can compactify this exponentially expanding future into a nice finite boundary, as long as you just have massless sources running around. And so this is the picture. Now, what about the Big Bang? Well, instead of saying the Weyl curvature hypothesis, Paul Todd, my colleague and student, originally had this better way of phrasing things in terms of the fact that you can stretch it out and form a nice boundary. I should explain that the ontological status of the two is very different. The future boundary, squashing it to a nice boundary, is generic. As long as you just have massless fields in the future, the past boundary stretching out is a very strong condition. We want a strong condition because we want a condition that makes the Big Bang this very special thing we seem to see. So that's the picture. I should say, is this picture, it's a nice geometrical picture. What about physically? Well, physically, you preserve the light cones. What about the, the mass and so on? Well, you see, we do have massive particles in the future. We have hydrogen, we might have stray electrons and positrons and things like that. We might have protons, maybe they decay into positrons. I'm going to postulate that there is, in the very remote future, a decay of mass, not decay of massive particles, that's not the point, the decay of mass. So you can have charged particles, the mass fades out until in the asymptotic future they become massless. That is an assumption, and the sort of basis of this is that when you look at when you have a cosmological constant, you might say that the Poincare group has to be replaced by the de Sitter group. The de Sitter group does not have as its Casimir operators the mass as one of them. So you might say, well, perhaps mass decay is not so implausible. And that's a point of view I would take. It would need more study to see how to make that make sense in view of particle physics. But that is the picture I have. And I should say also the squashing down of infinity, you might say it's very cold and very rarefied. Squashing it down makes it denser and the temperature comes down. What about the Big Bang? It's very hot and dense. Stretching out makes it much colder and much more rarefied. And they look really rather similar. Okay, well, this is not such an outrageous picture. What is outrageous is the next picture, please. Can I have the next slide? That picture is really explained. This picture of conformal cyclic cosmology, where our Big Bang is not just conformally like the remote future, it is the remote future in this picture of a previous eon. So this middle one is our eon. There was a previous eon, there's an eon to the future of ours, and so on. One point I should make about inflation is that I don't need inflation because many of the reasons that people want to have inflation, such as the scale invariance in the microwave background and so on, and correlations outside the horizon size, various things like that are explained because you have a sort of inflation. The inflation is the remote exponential expansion of the previous eon. It's not something you tuck in after the Big Bang. It's something which occurred before the Big Bang, and it doesn't need a new field. It's there already because of the cosmological constant. Can I move on to the next slide, please? Here I have this middle line represents the crossover between one eon and the next. And I want to point out that signals can get through. You could have photons getting through, provided the wavelength is sufficiently spread out, and you certainly could get that. You could say magnetic fields, for example, could get through and have an impact on the next eon. The more important thing is gravitational waves can, in a certain sense, get through too. So massless things could get through from one eon to the next under appropriate circumstances. Can I have the next slide, please? Here I want to show the first signals that I was interested in exploring. Here in this picture, the middle red plane here is really a three-dimensional surface, which is the crossover from the previous eon to our eon. Our eon, our past light cone, is in red here. That's us at the top looking back. At the bottom, we see two supermassive black holes colliding, and there are, or three eventually, because I'm having two different collisions, bang, bang, another one. And these would be signals which you could imagine we could still see. Also, if you see repeated events like this, you would see this would look like a circle in the sky. According to the analysis done by my Armenian colleague Vahe Gerzajan, you would see low variance, a ring of low variance. And that was what he looked for. But he looked for a strong enough signal, you were to see for concentric rings. You see, if you see in the galactic cluster, you would expect to see several of these impacts between supermassive black holes, and they would look like rings which were concentric. So that's what he looked for, at least 3 concentric rings to get a significant signal, which are low variance. Can I have the next picture, please? This maps the centers of these low variance rings. And what's rather striking, extremely striking in my view, is the very strong clumping of these signals. It tells us that at least in the previous eon, according to the analysis that I'm describing here, if it's not the real explanation, I would like to see another explanation. These points are singled out because they are the centers of rings, concentric rings of low variance. Now, a point that I want to make is that these are not just crowded in angular distribution, that is clumped here, here, and here, but they are clumped also in color. Now, what is color? That is the temperature. Now, the red ones, well, it's all confusing because red actually means cooler. Sorry, red means hotter because of the color coding, it's hot. Blue means cooler, so red means blue shifted and blue means red shifted. It's also confusing because in CCC, the model, you have to look at it carefully, but the ones which are more distant would actually be the blue shifted ones, and the ones which are closer would be red shifted. So the ones at the top are relatively close, that's to say inside our past light cone, or inside what we call our particle horizon. So we should see something out there very, very distant in our own eon. I don't know if people have looked carefully. There might be something out there, concentration of a lot of quasars or something. In the other picture, this one is red. That would mean outside our particle horizon. It's possible to see outside our particle horizon because our light cone extends back into the previous eon. And so you still get information from outside what is in our normal discussion outside our particle horizon. I should say these pictures don't make any sense if you have inflation. Inflation would stretch the join between one eon and the next, and you wouldn't get any signals at all like this. So inflation, in my view, has to be the exponential expansion of the previous eon. Can I move to the next slide, please? The other signal that I want to discuss here is the, well, Hawking evaporation of a black hole. Eventually, after really big ones, you expect to have to wait something like 10 to the 100 years or 10 to the 103 years, according to Don Page. The biggest ones may take that long, but still, you've got an infinite length of time, so that will still cause an effect. Can I see the final slide, please? In the final slide, this is a picture which is from our our paper. This is a paper by myself, Christoph Meisner, Pavel Mirovsky, and Daniel Ann in the monthly notices of the Royal Astronomical Society, published getting on for a year ago now. I'm not quite sure whether it's a year ago quite yet, but the bottom horizontal line is the crossover between the previous eon and the next. The top part of the picture, I should say, is just showing the amplitude of what we see. The bottom picture is a conformal diagram where we see previous eon, crossover is this horizontal line at the bottom. Supermassive black hole comes out. It doesn't start to radiate until very, very close to the crossover. And then all that radiation, the entire mass of that supermassive black hole is dumped into that single, pretty well a point, which on the other side is even small, it's Planck scale, less than Planck scale size. So it's a point on the other side. That point spreads out through 380,000 years. This is decoupling or short last scattering, or they're more or less in the same place here. And that is where you would start to see something. So this enormous amount of radiation pours out in this picture and spreads out until you get something like a Gaussian. This is the distribution you see up here. And this is us looking back, and you wouldn't see it head on exactly. You would probably see cutting through it a little bit outside. But what you would see was something like a Gaussian, which is of greater intensity. And the analysis done, well, it was Christoph Meisner's proposal for doing it, and analysis in detail was carried out by Daniel Ann. And what was found in the Planck data was that these points do exist with a confidence level of 99.98%. With slightly less confidence, you can find where the locations of the strongest of these points are. And the 5 strongest points, this was for the Planck data. You look in the WMAP data and you find they're also there in the WMAP data, very strong points in the WMAP data. If you look in WMAP, you find a 6th point, which is just about as strong. Look back in the Planck data and you see it's there too. So I would say that those 6 points are good candidates for what I'm going to call Hawking points. The Hawking point is the bottom here, but what you see is it's spread out to 4 degrees across the sky. That's about 8 times the diameter of the full moon. I rather suspect if you had a planetarium which was shown in the microwave background with great detail, that you could probably see these points with the naked eye. That is to say, of course, with the microwave background tuned to visible light. Because the intensity increase is more than 10 times the average temperature variation in the sky. So it's something I think you should probably see. You might say, why haven't people seen these before? Because they haven't looked. Now, if there's another explanation for these points, I would be very interested to see them. I haven't seen such an explanation. It seems to me the evidence is strong, and that I think people should take these things seriously. There are other signals too, which people should look for. I haven't time to discuss these. Thank you very much.
Thank you, Roger, for a beautiful talk. Let's have any questions. So can we have some new people who want to ask questions? Raise your hand or just speak. If not, let me go to Igor. You've got a question?
Yes, thank you, sir, for the nice talk. Did you try to compare your model with astronomical data?
With the which data?
Astrophysical data.
With the
astronomical data.
I think he just mentioned the Planck satellite and
oh,
WMAP.
yes, of course. This is very much. Well, that's the whole point. This analysis was done using the Planck satellite data, and the 99.98% confidence level is exactly using that data. In fact, and analyzed in more than one way in the paper that we have in the monthly notices. We also looked at the WMAP data and find the same signals. I should say that I forget whether the 99.98 confidence level also applied to the WMAP data, but that was initially for the Planck data, and the existence of, I should say, when you locate the strongest points, this is using a different algorithm, so it's not so the confidence level there, I would say, is not so strong, exactly where you see them. The confidence there, I would say, is that the 5 strongest points in the Planck data are also in the WMAP data, and that the sixth one we find in WMAP is also there in Planck. So that I think that whereas the weaker ones may be questionable, the 6 strongest points I would say are pretty good in the data that we actually, yeah, we're looking at Planck data and we're looking also at WMAP data.
Roger, just as a follow-up, would higher resolution maps of the CMB help to strengthen the statistics? So,
I
for
would
example,
imagine, yeah.
the recent ACT measurements are quite spectacular and much higher resolution than either Planck or WMAP. So I don't know whether any one of these points is within their region, because if so, you would
that's
get,
interesting. How,
yeah.
I'm sorry, I'm just so ignorant. Tell me more about this.
I can do it offline.
Yes,
But,
please do. Yes.
yes, it's they're actually so precise now. They're able to see galaxies, individual galaxies in the CMB through their
that's wonderful. Yes,
effect on the So if you can make more precise predictions for exactly the profile of this,
there are other things one could look for.
Yeah.
Such as, I mean, you can see actual galaxies, such as dark matter distributions.
Right.
See, because in this scheme, and there are various things I can talk about, but in this scheme, you must ask, how is it that you get the temperature variations in the microwave background, the normal ones that people talk about?
Yes.
And they, in this scheme, come from the decay of dark matter. So this would be the decay of dark matter in the previous eon.
Right.
And these would produce signals which would have a scale invariance. Also, you would get something like the spectral index, because this would give you an estimate as to the lifetime. The lifetime would have to be something like 10 to the 11 years. And this would give you something like a spectral index of the sort that we see.
Have you written a paper about that, or is that just
Not about that? No, that's
okay.
not written. Yeah, that should be right. That's
very interesting. Thank you.
Yeah,
I had another sort of general question. You made a very strong statement that you don't believe quantum gravity has anything to do with resolving the initial singularity.
Yes.
I wondered, since we don't know, you seem to be assuming that quantum gravity effects are only important on small scales when you make that statement. Since we don't, why do you believe that?
Well, that's an
why did you give up on explaining the Weyl curvature hypothesis from quantum effects? Why did you give up?
Actually, strictly speaking, I didn't give up.
Okay.
Just that it depends upon not quantum gravity in the ordinary sense. You see, I think that, in fact, it's a lot of things like when people talk about there's all this stuff about the loss of information and regain of information in black holes and all that sort of thing. And I always believed that what one needed in combining let's say the combination of general relativity with quantum mechanics, which is not strictly speaking a quantum gravity theory, in my view, it would have to be involved with gravitizing quantum mechanics as well. Mm-hmm. And when I say gravitizing quantum mechanics, I mean dealing with the collapse problem, the collapse of the wave function, not the collapse of a
gravity,
material body. This is the collapse of the wave function. And I've for a long time believed this is a gravitational effect. So that what one really needs, and here I'm agreeing with you, one really needs a combination of gravity and quantum mechanics which tackles the big scale as well. And the big scale, that means the measurement problem. Okay. And so that is where we really should see the effects of gravity and quantum mechanics coming together in a new theory. Okay. And that's what we want, not simply dealing. I'm really agreeing with what you're saying, I think, because you say, why just the Planck scale? And I'm completely agreeing. It's not just the Planck scale.
Excellent. Okay. I will speak a little bit about this in my talk as it happens.
Oh, good. That sounds good. Yes.
Any other last minute question? Got a few more minutes, so please don't be shy. I can't see everybody's hands, but I'm sure somebody has a question. Are there any students? Please. It's a good opportunity to ask Roger.
Don't mind if it sounds silly, because my question, my answer
Exactly.
sounds silly too.
Exactly. Please go ahead and ask.
Can I ask a question?
Please go ahead. Yes, I can't see you. But could you say your name? Say your name.
I'm Sravan.
Okay, thank you.
Hi, you mentioned for the Big Bang singularity, the while is zero, you're considering the isotropic single case, right? But like there are BKL singularities and also, I mean, would you comment about that? Because it's not about resolving one singularity, right? You would like to resolve all the singularities, all the possible singularities.
Well, this is past type singularities. You see, the idea is that future type and past type singularities are treated by nature very differently. And this was the problem that, I mean, for a long time I struggled with that you want a quantum gravity theory, which is very time asymmetrical. And I really couldn't make sense of it. It's more like the answer to Neil Turek's question, that one has to look at modifying quantum mechanics as such, in a way. I wouldn't expect exact uniformity in the Big Bang either. It's very close to uniformity. And when I say the Weyl curvature is zero, it doesn't mean that derivatives of Weyl curvature are zero. And that is in fact what you would expect, because when you have in this last picture, for example, well, not the last, one of the last pictures I had, when you imagine gravitational waves coming from say two supermassive black holes in the previous eon coming together and producing a gravitational wave signal, that gravitational wave signal will come through and it will appear as a derivative, a normal derivative in the Weyl curvature. So it's not exactly zero. You will have irregularities of a sort of lower order. So it wouldn't be exactly uniform. And in fact, it can't be exactly uniform because you wouldn't get any irregularities coming about. Also, the dark matter in the theory has to come about. When you look at the equations in detail, you see that there has to be a dark matter distribution, which comes from, again, it would be derivatives of what happens in the previous eon. So you would expect to see some relationship between the detailed structure in the previous eon and what happens in the next eon. So it would not be exactly uniform. There would be probably, well, I can only say, this is not an answer to your question especially, but there's this curious fact, which I pointed out, that in Vahe's data, most particularly in Vahe Gursajan's data, you saw this extraordinary clumping of regions of supermassive black holes as they collide. Now, this would mean that you'd have quasars in the previous eon, which would be very clumped, which would seem to mean that in our eon, we would get quasar distributions which are very clumped. And there does seem to be some indication of that. I would like to know more. I think that's another very interesting area of exploration in this scheme, because you would expect to see clumpiness in the quasar distribution on very big scales.
Great, thank you. Massimiliano, I think you had a question.
Yes. Hi, my name is Massimiliano Rinaldi from Trento in Italy. I would like to ask if this repetition of eons, as you call them, would that produce an accumulation of stochastic gravitational waves from one eon to the next, and so maybe becomes really large?
They wouldn't get bigger. They get weakened in a sense. As the gravitational waves across, in the first place, as I say, it's only the normal derivative. It would be very interesting to see actually testing gravity. You see, the analysis that Vahe Gursajan did was not to see the gravitational waves themselves, but the effect they had on the on the uniformity, the variance in the temperature. It would be interesting if you could detect the gravitational waves directly in some way in the next eon. They would not be strong. They would be very, very weak. They would get weaker as you go through, mainly because you're only looking, well, they get spread out. And as they get spread out, they get weakened. So there's no question about that. They wouldn't get stronger. but they would also be weakened because there is this effect on the where the conformal factor works on the Weyl curvature, and you get two. I can't go into the details of this, but there is a weakening as it goes across. So they certainly don't get stronger. They would get weaker.
Thank you.
Interesting if one could even see them, the weakness that they have. That would be really interesting.
Okay, unless there are any other questions, I think let's thank Roger.